Hello, my name is Shirley Portugal. I'm going to introduce you the final project for the course of wireless communication. The project is called Analysis of OFDM Modulation and MIMO Spatial Multiplexing Techniques on an IEEE 802.11n. This slide shows the system structure for the physical layer of the IEEE 802.11n standard. We can observe that the system is composed by different blocks. The first block is the channel coding. IEEE 802.11n uses channel coding with different rates. For the purpose of this simulation, we use just like 1/2 as the channel rate. Then the bits are modulated using phase modulation. This standard uses three kinds of phase modulation: QPSK, 16 QAM, and 64 QAM, although it uses VPSK but only for the pilot subcarriers. Then the MIMO block will distribute the frames through the different transmit antennas of the MIMO system, because each antenna is going to transmit simultaneously a different frame of data. But before they are transmitted, this data need to be modulated through the IFFT. What it does is that transform the signal to the frequency domain to the time domain. So, and we also need to add a guard interval so to avoid the signal interference, like intersymbol interference that I will explain later. At the receiver end, after removing the guard interval, we will perform the opposite. Sorry, there is a mistake here in the picture, but you have to perform the FFT. Then the data frames are gonna be like yes, united, let's say, combined, and then they will be passed through the digital demodulation and finally channel decoding. In this slide, I show the constellation for the different M-area modulation. As we can see, the QPSK modulation have more room for decision making. So this means that the BER of the QPSK is much better than 64 QAM, for example, because if we add noise to this symbol, even the symbol is not located at the right position, we still have a very good chance to recover this symbol, and to recognize it as the right symbol, and therefore having less errors. But if we see the constellation for the 64 QAM, we see that they are very close to each other, so very small amount of noise will definitely cause confusion, and it will be very easy to make mistakes in the decoding when the SNR is low. However, the advantage of using 64 QAM is that we will have a higher data rate, because each symbol is carrying 6 bits. So we will have a higher data rate compared with the other schemes. But then, so there's this trade-off. So we should use high order modulation schemes when we have a very good SNR. So here is to corroborate what I just said. We see that the ESNR of the QPSK is very good compared to the 64 QAM, and is much better than the 16 QAM. This is only for the AWDM channel. So this is what the receiver will, the errors at the receiver when there is only noise present. So in this case, we are not considering the fading, the effects of like a channel or interference. So now I will explain why the OFDM modulation is very important now for the new generation communication systems. I mean, the the advantage of the OFDM is that it divides a like a high um, data stream into parallel low data streams that are transmitted simultaneously over n subcarriers. So for this, for the purpose of this standard, we will say like the each OFDM symbol will have 64 subcarriers. The receiver will be able to demodulate each of the signals and avoid inter-carrier interference because they are orthogonal with each other. And we can see here that when a signal is transmitted in a wireless environment, the multipath components of the channel, so that are caused by the reflections from buildings, trees, houses, etc., they cause inter-symbol interference. To avoid this problem, we insert a guard interval in front of, like, at the back of the symbol. So the the time of the symbol will be larger than the delay spread of the channel. This this guard band, which is also called the cyclic prefix of the channel, and it's of the symbol, sorry, and it's very important. It will add some like extra length to the symbol, but it is very important to avoid this inter-symbol interference. So here I show you the OFDM frame structure for the OFDM. It can work at 40 megahertz. I'm working here for my simulation with just 20 megahertz. And yeah, each subcarrier will have like around 312 kilohertz. Yeah, as I mentioned, BPSK is only used for the pilot. Pilot, they have a very specific position at -21, -7, 7, and 21 subcarrier. The other, like 48, are data subcarriers, and there will be around like 12 subcarriers that are used only for like null. They are null. They are not used. So the total subcarrier used are 52, from which only 48 are information. The symbol will have also other. There are also other like areas which are called like preamble, and they are used for channel estimation, but they are not important for the purpose of our project. So as we can see here, using the parameters for OFDM for the IEEE 102.11n, I simulated my system in MATLAB, and I added the cyclic prefix, which is equal to like 16 subcarriers, and the total signal duration is like 4 microsecond, considering the FFT period and the cyclic prefix. And we have here the performance. Of course, QPSK will be better, but we can see that with OFDM we can overcome the fading of the channel. So now I'm going to introduce to MIMO spatial multiplexing concept. So usually in a system, as I showed at first, OFDM and MIMO will be combined. But for purpose of simplicity, I just simulate them separately. So I can use the channel in the frequency domain to work with MIMO equalization. Otherwise, it is very difficult. It is possible, but it takes more time. So for spatial multiplexing, the number of the receiver antennas must be equal or greater to the number of transmit antennas. They are usually like, for the purpose of my system, I just use the same number for transmitter and receiver. So as we see here, like each receive antenna will receive like the frames transmitted from both antennas, and not only that, it will also like see different like, path, like the channel fading experience by each data frame is not the same. So at the receiver you have the combination, so it's like a summation uh, of this matrix. And here we can see a little bit better, like in mathematically speaking, it could be uh, expressed like this. So zero forcing, what it does is basically calculates like the inverse of the channel. But as we see here, when we create this filter and we just multiply it by the received signal, we eliminate the channel, but we will increase the noise. And as we can see here in this term. So there are other methods, such as the minimum mean square error, that they try to minimize the effects of noise. So they're a little bit more complicated, but it pays off because it improves the BER. And also there are another optimization methods like successive interference cancellation and ordered successive interference cancellation. So these are not linear anymore because, I mean, they are linear, but they use iterations. So the decoding of the channel, I mean, it becomes more complex. In the like for the case of successive interference cancellation, what it does is that it first decode one symbol. It tries to identify which is the symbol sent by the first transmit antenna. After it identifies this symbol, it will subtract the influence of this symbol and its channel path from the received signal, and then will proceed to decode the symbol sent from the second antenna and so on until it decodes the symbol sent for all the transmit antennas. What the ordered successive interference cancellation does, it does almost the same. The difference is that it will consider the channel conditions. So it will decode first the signal which have the best channel condition, and so the decoding will have like better performance, as we can see in the picture. And finally, I show the data rate that increases with spatial multiplexing. I have 2 by 2, 4 by 4, and A by A using 16-QAM with a convolution code of 1/2. I didn't simulate the maximum data rate, which will be achieved with 64-QAM because the convolution it doesn't use 1.5 rate for convolution code anymore. But I think this proves this proves in a very good way that that the data rate requirements for 4G or 5G technologies are only achieved with the use of spatial multiplexing and techniques like this. Otherwise, like if we just use like one antenna or 2 by 2, we will not be able to achieve the maximum data rate. So